Any questions from last time? Okay, here's kind of, we talked about purely inseparable, right? That means its minimal polynomial is a linear to some single power. We notice that if you have an element that's separable and purely inseparable, then it's in the base field in the first place. Here's kind of a cool little lemma here that I love this. When sits, and it depends on an observation that we made earlier. It's bolstered by that anyway. If F is an extension of K, and the characteristic of K is equal to P prime, if U and F is algebraic, well, let me change this into a red. If U and F is algebraic over K, then we complete. What do I mean by that? If it's not separable, I can make it separable in the following sense. U to the P to the N. And separable. Over K. For some N, whoops, some little n in natural numbers equal to 0. So in other words, U might be an element that is purely inseparable. If I take a large enough P to the N power of it, where P is the characteristic field, it cleans it up. So even though the element itself may not be separable, if I take a big enough prime power of it, it will be separable. Proof of this. If the degree of U over K is 1, then because it's already in K and it's already separable. Now suppose that F is the minimal polynomial, the non-set of U of degree greater than 1. Well, then poly, a non-separable element, and degree F greater. Then we've already proved this. Remember the derivative of this. So if it's minimal polynomial, if the element's not separable, it's got a multiple root, its derivative is exactly 0. Agreed? So as we discussed before, F is a polynomial x to the p. That is, every power of every term in a polynomial that has a non-zero coefficient, its exponent must be a multiple of p. So U to the P is algebraic. Over K of degree less than the degree of F. Right? Because instead of considering U, we now consider U to the P. That's algebraic by degree less than F. So by induction, u to the p, some p to the m power, to the m plus one is separable. So there, I didn't really mention my inductive step there, but I hope it's kind of clear. We reduce the degree of the polynomial and we got what we wanted. Okay, so I'm going to give you a couple of theorems here about the structure of how we can kind of dissect this notion of separability and pure inseparability, and then I'm going to talk about finding Galois. Yes.
What is the difference between like if F is separable versus splits over a field?
Well, splits means it just factors into linear polynomials, right? Separable means when it factors into those linear polynomials, they're all different.
Okay.
Right. Okay. Let F be an extension field of K, and here we're going to have the characteristic of K being prime. So suppose the characteristic of K equals P prime, and F, whoops, K is contained. The following are equivalent. Number one, F is purely inseparable of K. Number two, the irreducible polynomial of any U in F any U in F is of form x to the p to the n minus a and k x. So let me make the observation that this also covers all the elements that are already down in K, because if you take n to be 0, this is just x minus a, right? 3. If U in F, then a big enough power that's in K, in fact, prime power. Or the only elements of F that are separable of K are the elements of F. If U in F is separable over K, then U is in K. And finally, number 5, F is generated over K by a set of purely inseparable elements. Okay. Let me kind of talk our way through this. Suppose that F is purely inseparable over K, right? I guess we can use this, can't we? So let's note that if U is in F, then U to the P to the N is separable over K, right? But if we're under this assumption that f is purely inseparable, right? Then for this thing to be separable, it has to be in K. Right? Therefore, U to the P to the N equals K in K. And so we get that yes.
So from like the start, are we assuming that U is just in F, not algebraic?
Yeah, oh, we're assuming, you know what? I, I, I meant for this to be there, yeah, if it's purely inseparable, it has to be algebraic, so let me clarify this here. Yeah. I want this to be an algebraic extension, thank you. I want that to be out. So what I've shown here, if you have one, then you must be a root of a polynomial of this form. Now, why is the minimal polynomial of that form? See if you can think about why the minimal polynomial has that form. Of course, if you have two, then two immediately implies three, right? Because if this polynomial is in Kx and U is a root of it, that means U to the Pn minus A equals 0, or U to the Pn is in K, right? So, and this one right here, F is generated over K by a set of purely inseparable elements. Well, yes, so if F is generated over K by a set of purely inseparable elements, well, if you have that F is purely inseparable over K, then everything that's in K and not in F is purely inseparable. And so it's generated by everything that's not in K in itself. So everything in here is purely inseparable. On the other hand, the reason you can go back here is purely inseparable elements that close under addition and multiplication. So that's kind of an important piece of that there. Okay. Corollary. 14.4.8. Let's suppose that the characteristic of K again is P, and F is this time a finite dimensional purely inseparable extension. And F is purely inseparable. Okay, then the degree of the extension is P to the N. Why is this true? And this is correlated from this. So under the assumption here, this is finite dimensional. The real question is, why is this power of P? Well, no, let's let U in F be arbitrary. Then notice that the minimal polynomial of u over k is a form What's that?
Oh, no, there's just a mile.
Therefore, okay. So only divisors actually let me call this PDR. There's no, every intermediate extension has degree over k, a power of p. Therefore, since it is finite, no other prime can divide the intermediate extension, right? If there was, so here's another way to do it. Right? If you don't find that convincing, suppose there's a prime other than p that divides this, right? So that means that you should be able to find an extension that has that prime in it, right? A finite extension, right? And therefore you would have to find an element that is not of this form, because every element in this intermediate extension has degree a power. Right.
Why do they make it p to the r instead of p to the n?
Well, because there might be a whole bunch of different ones. They're not. Right. How about that? Yeah, I just didn't want to use the same answer as the theorem until the end. Yes.
If we have f equal to k, then can
Yes. P to the 0.
be okay,
Yeah. That equals k. Yeah.
right? But could it be purely inseparable?
Yes.
Okay.
If it, yes, any F is F is an extension of itself degree 1 that is both separable and purely inseparable. Okay. Okay, so here, this is kind of a dissection theorem, and I think touch with this here. This is what I wanted to show you. I'll leave this kind of mostly as an exercise, at least for you all to go over. Think about. Let F be an algebraic extension of K. So let K inside F be algebraic. I am going to denote S the set of all elements of F that are separable over K, P the set of all elements of F that is purely inseparable. All separable elements over K P set of all purely inseparable elements over K. So, number one, let me point out that, at least this makes this much sense, P and F also. Notice that S contains all of K, and P contains all of K, so at least it's got that going for us. So number one, S is separable, exceeds K. So the set of separable elements forms a field, and it's a separable extension. F is purely inseparable over S.
Dr. Gordon,
Uh-huh.
is one supposed to be like, we're considering it has to be a field? Like it's a
It is a field.
It's an extension.
P is purely inseparable over K. So here's kind of the situation we've got going on thus far. So we've got this base field K, and we've got this algebraic extension F, and then we have the separable elements, the purely inseparable elements. These are all field extensions. This one is separable. S inside F is purely inseparable. K inside P is purely inseparable. Got one. P intersect S is equal to K. And 5, F is separable over P if and only if F equals SP. And 6, if F is normal over K, then S is Galois over K. So if this is normal over K, remember what that means is every polynomial in Kx that has a root here actually has splits there. Every irreducible polynomial that has a root there splits. Then S is Galois over K. F is Galois over P. Right. Yes, in the case, let me put this so. This is a separate thing. This depends on that being normal. F is Galois over P, and the Galois group of K S over K. These are all the same. So all the relevant Galois groups are essentially the same thing. Okay, there are further results about this. If you're interested, you can break this up into separable degree and inseparable degree and so forth. I'm gonna skip over this a little bit and we're gonna talk a little bit about approaches to finding Galois groups to a polynomial. But any questions on that? Yes.
With that extension F to P, is that like separable or purely?
If and only if F is equal to SP.
Okay.
So if you put these animals together and you get F, then the answer to your question is yes. Okay, so this is kind of I do this for kind of fun. We're going to do this and then quickly go through finite skills and then start talking about arithmetic rings. So this is just kind of a fun section. Approaches. So I want to show you some tricks to the trade, especially for small degree polynomials, just for fun. So I'm going to show you some groovy tricks. And the culmination of the section is I will give you a technique that will always work for any polynomial. And you'll never ever want to. The only time that you should ever use this is if you get sent to hell and Satan says, here's this big polynomial and you've got eternity to do it. And once you solve from the Galois group, I'm going to let you out of hell. Then it might be worth it. Other than that, it's very cumbersome. You'll see. I mean, it's even hard for quadratic polynomials, but it always works. And so I take some little desert island comfort in that. So let's get started with this proposition. Let f of x be separable, irreducible. So I usually think that I'm characteristic 0 here, although I don't have to be, and then everything's separable. Separable if you're irreducible. Let f of x and kx be separable, irreducible. Polynomial degree n. So then the splitting field of F is a Galois extension of K. So it turns out that any splitting field is normal. And so if you take the splitting field, this would be normal separable. So the splitting field of F is Galois over K of degree less than or equal to n factorial. Right? Because that's true of any splitting field. What is more, I'll tell you a bit more. What is more? N divides the order of the Galois group. F over K. This is always true. And the Galois group of F over K is a transitive subgroup. Of S. So let me kind of review what needs to be transitive. Anybody remember what it means to be a transitive subgroup of SN? Think of SN very practically, right? Like acting on 1, 2, 3 up to n, right? So,
Oh, is it, just transpositions? Or
no,
generated
not
just
quite. 1, 2, 3. J. Okay, so SN acts on itself. In fact, a very popular way to write elements of SN is product of disjoint cycles from SN, right? A subgroup H in SN is transitive if for all the I there exists sigma in H such that sigma I is equal to J. This is what it means to be transitive. It means take any two numbers out of that set from 1 to n, call 9j. There's something in that subgroup that'll take I to j. I'll give you an example of a transitive subgroup of SN. All of SN, because the transposition IJ works, right? And I know that the transposition IJ is in SN, right? Here's another one that works. AN is a transitive subgroup of SN as long as n is at least 3, right? Because it turns out that AN contains all the 3 cycles, right? 3 cycles are even transpositions, right? Or it's not. 3 cycles are even permutations because it's product of 2 transpositions, right? So AN works too because and you need at least 3 because if you want to take IJ, then pick some A that's not equal to IJ and do this. All right, there you go. Am I okay with it? But there are others. Sometimes. Well, you know what? I'll even toss. I'll even start here because I'm not going to look at S1, right? Because polynomials of degree 1 don't need to be factored, but polynomials of degree 2, I mean, this is the bane of every high school sophomore, right? Learning the quadratic formula, right? But we know at this point, from our perspective, it's easy. What are the transitive subgroups of S2? Well, A2 is just the identity, right? Not transitive. S2 itself is the only one. This is one of the reasons solving quadratics is, from a certain perspective, easy. What are the transitive subgroups here? Well, S3 and A3 are the transitive subgroups of S3. The only other subgroups of S3 are the identity, which is clearly not transitive. And these subgroups of order 2 that are just generated by 2 cycles, right? But or transpositions, right? And so like one of the subgroups is the identity of 1, 2. Well, that leaves 3 completely out, right? So all of those are intransitive, right? The cubic equation is not terrible. How many transitive subgroups? This one there. Oh, you didn't answer it fast enough. I'm gonna take the easy ones. Are there others? I'm gonna come back to that one. Let me point out that any subgroup of SN that contains an N cycle is automatically a transitive subgroup. Why is this the case? Well, let's just, I'm gonna do it easy here, 2, 3, I, J, N minus 1. I claim that if you have a subgroup of SN that contains an N cycle, it has to be a transitive subgroup. Well, suppose you want to take I to J, right? If they're next to each other, you're done. What if they're not next to each other? You can certainly rewrite this way. This might make it easier for you. It doesn't matter where you start a cycle, it's the same thing, right? If I and J are adjacent, then you're already done. What if it's IAJ?
You do it twice.
That's right, if you do this twice, that'll be in there, that'll take I directly to J. More generally, if there are in things in between it, you just take this to the, that power, and it'll do that. Everybody, well, in things between it, just take this thing to the N plus 1 power. N is a terrible choice. There are in things in between there, you take the N plus 1 power. I agree with that. So if you've ever got an N cycle in there, it's got to be a transitive subgroup. So let's go back to S4. You think subgroups of S4 that have an N cycle in it? Well, there's a cheap one. Cyclic of order 4. Just take your favorite 4 cycle and see what it generates, right? By the way, each one of those cycles let's see, if you square a 4 cycle, it's a product of 2 cycles, right? And so how many 4 cycles are there in S4? I guess there's 6 of them, right? And every 2 of them correspond to one of these 6. So there must be 3 subgroups of order 4 that look like that, but they're all transitive subgroups, right? So really what I'm doing is isomorphism. There's only one subgroup that's isomorphic to S4, one that's isomorphic to A4. There's a few of them that are isomorphic to generated by a 4 cycle. What else? Can you think of another one that contains a 4 cycle?
With D4 somewhere.
There you go. D4. Right. 1, 2, 3, 4. So this is generated by 1, 2, 3, 4, and the cycle 2, or in the transition 2, 4. All right, that's one way of doing it. And that gives you a little D4 in there. And there's another. Your cue, Chantilly.
Z2 press C2.
Which one? Here's the maddening thing about S4. Let me give you a Z2, Z2. Nice. There are several variants on this, right? I could do 1, 3, 2, 4, and then 1, 3, 2, 4. I could do 1, 4, 2, 3, and 1, 4, 2. Is that transitive? the one I've got written up there, is not transitive. How in the blazes are you ever gonna get one to go to three? Right, 1 to 2 is good, 3 to 4 is good, but one going to three, you're out of luck, right? So, should we all be teasing Chantanou for his inglorious misstep? Or is there more here? There is a C2 that works. It's just not this one. That one looks like it doesn't even work, right? Because is it clear that this is I mean, certainly these elements are all of order two, because they're disjoint, they're a product of two disjoint transpositions. But it's not even clear that the product of these two is still in here. But in fact, do the multiplication out, you will see that it is like this. If you multiply these two, one goes to 3 to 4, so there you go. 4 goes to 2 to 1, perfect. 2 goes to 4 to 3, and so forth. So this times this is this times this is this, and this times this is this. This is another Z2, Z2. That's not clear, is it? This one is transitive. But not just any Z2, Z2 subgroup of this two. It's just this one right here. All right. Do you know what's another difference between these two? Normally, I don't like to wait too long for questions. This one, probably. That's kind of weird, right? Because this one here is a normal subgroup of A4. And the reason I know that is because when you conjugate any element in Sn by another element, you get something of the same cycle type. And these are the only things in this cycle type, that is a pair of disjoint two cycles. So any conjugate of this has to end up in here. This one's normal, this one's not, because for example, 1, 3, 1, 2, 1, 3. If you conjugate this by 1, 3, you get 1 goes to 3, 1. You get 2 goes to 1, 3. Yeah, that's what you should get. So this, the ones that look like this are not normal, and the other one is, right? But this is kind of a little magic. There's the transitive subgroup. There's one that's isomorphic to it. New transitive subgroups, that's 5, are they?
S1, A1, D5.
There you go.
Order 20,
How about them apples?
and then Frobenius group of order.
Ah, how'd you know that one?
You studied in the last exam.
Oh, yes. Right. We don't see this one come up. This is generated by 5 cycle and 4 cycle. It's got a normal 5 group. And it's got this other CELO subgroup that's cyclic order 4. How about there's 16 transitive subgroups of S6. 7 of S7. And I think I could guess some of those, right? There should be an analog of this one, probably. Yeah, there'll be an analog of this one. I guess we'll need a couple more. Should figure that out sometime. Fine. there's 50. And when I say 50, I just mean up to isomorphism, right? Because some of them, they have automorphic images that are also transitive, I guess. And so and just for fun, S12 is rather complicated. Up to isomorphism, there are 301 transitive subgroups of S12. Okay. But at least we can conquer up to 5. I know that. Okay, any questions?
Does this mean, cause like we're gonna use this to argue something about solving polynomials of this order. Does this mean that, like, if we could write a general formula for like a 7th degree polynomial, that it would be easier than writing a 6th degree?
Well, I mean, a lot of 6th degree ones, like for example, if you have a 6th degree polynomial that only has non-zero terms, degrees 6, 3, and 1, that's always solvable. Right, because what you do is, the first thing you do is you take the cube root of that, and it's quadratic.
Sure.
If you have a 6th degree polynomial that has only even, that all the odd degree terms are missing, that's always solvable. Because substitution, x equal u squared reduces to a cubic, which is always solvable, and then you just extract an appropriate square root. Up to 5, if you get any of these Galois groups, with the exception of these, you will be able to solve the polynomial in terms of radicals, right? And in fact, we've not completely, but sort of done something. If you look at this polynomial, one of the roots is the 5th root of 2, and that's a radical. And you can extract all the other roots in terms of radicals, right? So if you get, so in other words, the Galois group for that polynomial has to be one of these 3. If you get one of these 2, then you lose. It's got solutions. It's just you can't write it in terms of radicals, sums and products, things like this. And I'm here to tell you that if you make up a polynomial with rational coefficients at random, that's the Galois group you're going to get. It's S5, right?
This one is C5?
Nope. Venus group 420. Okay. Definition. 3. I'm going to start by defining the discriminant, which is something that you all probably heard around the campfire before. Let f of x be a k of x and characteristic is not 2. So I'll avoid that here. Suppose that n is the degree of f and f has indistinct roots in some splitting field of k. And notice I'm not demanding that it's irreducible. I just demand that it's got n distinct roots in some splitting field over k. Splitting field of f over k, of course. We define delta let's call it I less j or I'm sorry, j. Where, let me explain what these are. R1, Ri, Rj, Rn are roots of f. So this is just the product of Ri. We put the roots in some order, and this is just the roots Ri minus Rj, this product for I minus j. And the discriminant of f of f is, the discriminant of f is d, which is delta squared. It's just the square of this. And that is good for today. Any questions on it? We'll talk about what all this means later. Questions? Okay, I will see you folks by Wednesday, if not in 5 minutes.